kind of an introductory session to Amazon DynamoDB and kind of how you can model your data um, when you use that database. Okay, let's get started. Okay, so before like jumping onto what DynamoDB is and stuff, so like let's try to answer like a question. What problem DynamoDB actually solves? So the problem is the relational databases don't scale very well when you go to like top of the limits. So if you consider a scenario, let's consider this. So like when you get started with like a new application or something, so like you might have something like this. So like you have a relational database, you have like about 10 gigabytes of data, and you do like a kind of a bit of a complex query, but like you have like few joins, group by and stuff, and like but like your response time at the database level is like 5 milliseconds, very acceptable, so nothing wrong here. But when your application grows, maybe like 1 year down the line, now you have more users and you have more size for your database, and when you try to do the same query, your like response time has increased because like you have a lot more users using your system, and so like there's a lot more traffic. And if you go even further, maybe like couple of years down the line, now like you have like a huge amount of data, and you have like your like a platform has grown, and now you have like multiple applications and things like that. And now the same query is like takes like 2 seconds at the database level. So now this is kind of like an unacceptable scenario, because like uh, the point at where you are, like you have maybe like you have millions of users, and then like you have thousands of concurrent users, and like if you consider like this like an e-commerce platform maybe, and like a few seconds can mean the difference between like a user getting irritated and not like purchasing something. So having like consistent performance when you scale is very important in these kind of use cases. So okay, so let's like look at like one more example. Like so what are like the main reasons for this? So one of the things is like poor time complexity, characteristics of the SQL joins. So it depends on how you write your joins. So like it can be like you can write it in like a kind of efficient manner, or like it can be highly inefficient. So and with like how many like with the traffic and all the sort of scenarios, like it can be like you can't predict. So you can get good response times, maybe you don't get like some of the time you don't get. And the other thing is like relational databases, it's very difficult to horizontally scale. It's not impossible, like large corporations like YouTube and uh, companies like that, they do this. I think like YouTube is based on MySQL, and but like for a normal company, like it's kind of hard, and like people who know these things very well, like the skilled people are very rare, and like they're expensive. But also like if you try to do this yourself, it's very hard to manage. So your only alternative is to vertically scale, but there's limits to that. So like at one point, like you might be spending like a lot of money because of this issue. So, and the third one is the unbounded nature of the query. So what does this mean? So let's look at an example. So let's see about this query. So like you are selecting some data, and you're doing like aggregation function operation, group by, order by, and like a limit. So within this query, like things you have to do, like you have to scan the entire orders table. you have to group the orders by the user ID, and then you have to sum the order amount by the user to find the total. And you have to then order the results of the previous step according to the sum total, and then you have to return the top 5 results. So this is like if you consider this, like when you break it down, this is kind of a taxing, like it's like taxing a lot of performance. And like you don't just get one of these, like when you have millions of users, you get like thousands of these concurrent requests, so like it becomes very hard. So that's why that's one of the reasons why Amazon came up with DynamoDB. So let's look at how they describe DynamoDB as. So according to Amazon, DynamoDB is a fully managed serverless key value NoSQL database designed to run high performance applications at scale. And DynamoDB also offers built-in security, continuous backups, automated multi-region replication, in-memory caching, and data import and export tools. So let's try to dissect this and see what are like the actual features that DynamoDB offers. So the first thing is like, as it mentioned, like it's a key value database. So what does this mean? So the data is stored as like a collection of key value pairs. So each key serves as the unique identifier for your data. So you have to retrieve your data by your key. So you can't just go and get some of the data itself. So you have to use the key always. And this is specifically built for like online transaction processing operations. So like you got two types, like online analytical processing and online transaction processing. So like OLAP, so that is more towards like analyzing large data sets, kind of ad hoc queries and stuff. Maybe do like mostly it's analytical stuff. So this is not built for that. This is only built for like OLTP, which is like at a time it's concerned like with few records or like maybe one. Uh, and it's fully managed and serverless. So it's managed by AWS. Servers are managed by AWS. You don't even know like where the servers are. So you don't have to do anything. And it's also schemaless. So what does like so in DynamoDB, like you have to only define your key, and your items can take like any structure. So like yeah, you are not limited, like you're not maybe like if you use SQL, like you're predefined by your database schema, like you are limited by that. So in DynamoDB you don't have that. And it's also like provides a HTTP connection model. So when you consider like normal relational databases, uh, they provide like a consistent TCP connection. But on DynamoDB, like every request is like a HTTP request. Every request to the database is like a HTTP request. And it also provide IAM authentication. So like in so you can limit like what are the actions that can be performed and who has the authorization and those sort of things. And so one of the like the claims is like there's no performance degradation when you're scaling. And this is one of the main like big ones. So this they claim to like deliver sub 10 millisecond response times at the DB level at any scale. And so we'll talk about more on this later. And they also provide flexible pricing. So you have on-demand pricing and provision pricing models. And also they have automatic replication. So like your data is stored in uh, like each one of your data is like stored in 3 storage nodes. So you have like the durability and the availability because of that. DynamoDB also support multi-region with what they call global tables. So if your user base is like kind of spread across the world, so maybe you can utilize these features, and also provide encryption at rest. So this can be an important thing, because like some of the applications uh, like by the country's law like requires some data to be encrypted at rest. So doing that yourself is going to be more harder. So if you want like a not if you want, DynamoDB always encrypts your data at rest. Also provides backup and restore functionality. So you have on-demand backup, and you also have a feature called point-in-time recovery. So with this, if this is on, like this charges more, but if this feature is on, you can restore your database in any point of time within the last 35 days. So you got like a sense of safety with that one. Mm, like DynamoDB also provides automatic data deletion using TTL. So this feature, so you can define for some of your items, like if you say, so this data is only, we are going to only store this for 90 days, and then we don't need that. So then maybe in a SQL database, you have to run some kind of a job to delete those data. But with DynamoDB, when you actually create the item, you can define time to live. So when that time passes, you have to provide a Unix epoch timestamp. But when that time exceeds, DynamoDB will automatically delete that item, so you don't have to worry about that. So you also have what you call CDC, change data capture, with DynamoDB streams. So it captures a time-ordered sequence of item level modifications on any table, and it stores in like a log for 24 hours. So you can like use this to supplement if you have like event-driven architectures like Lambda triggers or something. This can be useful. It also provides, like if you have read heavy workloads, DynamoDB also provides something called DynamoDB Accelerator, or DAX. So it's a fully managed and highly available in-memory cache. And with this, they claim up to 10 times performance increase, and response time decrease from milliseconds to microseconds, even at millions of requests per second. Okay, so after that, let's look at some basic terminology and things that we not have to know about this. So we got concept of tables, and we got primary key, item, attribute, item collection, and indexes. So these are kind of the basic stuff you have to know about DynamoDB. And so in this image, you can see first four things. So the table is the entire table. Item is like a record in SQL table. So this thing, uh, and the primary key is what you use to like look up your item. So in this case, like this is called like a simple primary key, but there's also like another type called composite primary keys, and we'll talk about the differences in a while. And also you have attributes. So these are actually like your data. So your key is only like supposed to use like help you to find the item, but these are the actual like the data. So those are called attributes. Okay, so let's talk about the primary key. So you have two types of primary keys. First type is the simple primary key, as you saw, and you also have something called a composite primary key. In simple primary key, you only contain a partition key. So we'll talk about what the partition key is in a while as well. But uh, in composite primary keys, you have two types of keys. So you have the partition key and an additional key called sort key. Sometimes these are referred to as hash key and the range key, but the official terminology is partition key and the sort key. So let's look at an example. So here we have a different kind of table, and you have your partition key as actor and sort key as movie. So like if you have like a common partition key, so you can kind of put together your items in this manner. So for Tom Hanks, you have 2 movies. So if you want like a to get just the movies that Tom Hanks was in, you can use this way. Uh, so this provides more flexibility. So this like a very simple example, but kind of when we go forward, you'll see like what are the advantages of having a composite primary key, and it's kind of the always the recommended way of doing things. Okay, so then we can move on to the supported data types. So there's 2 types of data. You have scalar types like string, number, boolean, binary, and null. And you also have document types, map, list, and set. So these are the only supported data types by DynamoDB. And one of the important thing to keep in mind is like your key, although DynamoDB supports all of these data types, your keys can only have these 3 data types. So it can be either string, number, or a boolean. So usually like you'll see like a like lot of use cases you are going to use a string as your keys. Okay, so what is the item collection? So if you are like a set of items has the same partition key, it's called as item collection. So this can be useful for partitioning. We'll see about that as well, and data modeling. So in this example, the same thing. So this entire thing is an item collection because they have a partition, like the same partition key. This single item is also like technically we can call as an item collection because like it's the same partition key. Okay, then we'll move into indexes. So in DynamoDB, like indexes work a bit differently. So you can use indexes to reshape the data and support different access patterns that you cannot support with your base table. Uh, so we'll talk about more on that, but mainly like there are 2 in types of indexes. You have local secondary indexes and global secondary indexes. So in local secondary indexes, you use the same partition key as the base table, but a different sort key. But in global secondary indexes, you use like different partition key and a sort key. So it's kind of entirely different from your base table. Yeah. So we will see like, but most of the time the global secondary indexes are preferred because there are some limitations when using local secondary indexes. Okay, so this example, so like you have the same table that we looked at before, but now we have a use case. Like remember, like we can't get this directly, so that's the whole point. So now we want like to get things by the movie, but we don't have that in the base table. So what we can do is like create like a global secondary index where we flip the keys. So now in this scenario, now if you want like the actors who have been Toy Story, you can get that directly. So that's sort of how you can use uh, global secondary indexes to reshape your data. Okay, so what happens under the hood? So how does DynamoDB guarantee this consistent performance? So it does that by sharding your database into partitions. So this is sort of thing like you can't do on a like you can't easily do on a SQL database. I think there are some solutions, but they're like very difficult to implement and need a lot of expertise. What happens with DynamoDB is like you got something called partitions. So you have the partition key, and based on the partition key, your data is split into sort of different partitions. And it's in simple terms, it's like a distributed hash table with a B tree. I put this in parentheses because like it depends on whether you have a simple table where like you have only like the partition key, or you have a composite like a table where you have the both keys, the partition key and the sort key. So this obviously helps with the horizontal scaling, and each partition can store up to 10 gigabytes of data, and each partition contains 3 nodes, or like 3 storage nodes. So you got the primary and 2 secondary nodes. Your writes will always go to primary, and in the next slide we'll see like how that works. Also, like if by any chance like this amount exceeds, now your partition has to have more than 10 gigabytes. So DynamoDB has something called auto admin, that it will provision like another partition for your key. So that happens under the hood automatically, so you don't have to worry about that. So what happens? So like if we consider this, so first what we have established is we need the key. So first thing is like, so since we have split the data into different partitions, so when you need to get an item, you need to know where that item resides, in what partition. So the first step is you need to find the storage node where this item is located. So for that, you use the partition key. So it's a hash. So you hash it, and it's always going to be like a constant time operation. So to find the partition where your data is. And then if you have a sort key, then you have a B tree in your partition. So B tree is like a tree data structure where the items are lexicographically sorted, so always sorted, and you need to find the item. So you need to find like from the starting value of the sort key, you need to compare. And for this, the time complexity is going to be O log n, where n is the size of the item collection and not the entire table. So you have like, since you have split it into partitions, you're now only concerned about that specific partition. So yeah, and then you have to read the values until the end of the sort key match. And so this is going to be like a sequential read, and there's a limit to that. We'll talk about that in a while. So it only returns up to 1 megabyte of data. But if you see this chart, you can see that both of these operations that we talk about are in this excellent region. So very, very minimal response time. So by using this architecture, it's the way that DynamoDB guarantees this consistent performance. All right. So what happens when you get a request? So DynamoDB has something called a request router. So that is the one that will like point where your data actually is. So if you get like a put request, and this is the key, so it'll hash it and identify that okay, this must go into this partition, and then so you write, so like you have a write operation, you write the data, and then also it will replicate the data into the first of your 2 secondary nodes. And if this is successful, then it will signal the request router that this write has been successfully completed. But you also got a third node, or your secondary storage node. Secondary, yeah. So, but now like you have a situation where your data is not in sync. So these two has the most updated data, but this third, sorry, this third partition will not have the most updated data. So this is where we talk about the eventual consistency, where like in between the time you get to replicate from here to here, if you do a read request on the item that you just wrote, there's a chance that you might read from for the read request, the request router will split your request into one of the three different nodes depending on the load and different parameters. So there's a chance that the request router will redirect you to read from here, and you'll be reading stale data. So one out of the 3 times, there's a chance that this can happen. So that's why like it's a, you say like eventual consistency. And what happens is then after that was a successful, the primary node will asynchronously replicate the changes to your third node, and now all the 3 storage nodes will be in sync. So usually happens in milliseconds, they claim, but there's some scenarios that can take some time, and so you need to, like, it depends on your context whether like you need to always have the latest updated data, and there's a way that you can guarantee that, like DynamoDB provides strongly consistent reads, as they call it, so that a strongly consistent read will always read from the primary, so you always have the latest data. Okay, so let's talk about bit about pricing. So you have 2 units where DynamoDB, how they charge, mainly how they charge you. So you got the write request unit, or WRU. This represents one write for an item up to 1 kilobyte in size. And you also got read request unit, it's called RRU. It represent, this is the thing that we talked about, one strongly consistent read, or 2 eventually consistent reads for an item up to 4 kilobytes in size. So if you want strongly consistent, it'll cost you more. Yeah, but eventual consistent reads are cost half as much as a strongly consistent read. So this is kind of I captured from the DynamoDB website on AWS. So as you can see, the pricing, first thing you can see is like reads are very cheap. In DynamoDB, writes are more expensive, but altogether, like they're in the realm of millions. So even if you have like a lot of user base, if you need like a cheap solution, this might be like a good choice depending on your context, as always. Okay, so let's talk about some of the limitations DynamoDB has. So one of the main things is there's a max item size. So it's at 400 kilobytes. So you have to always be sure that you are not storing an single item, which can exceed this amount. So this is why you have to be kind of very cognizant of how you how you model your data. And the second thing is, it will only return like for queries or scans. So scanning is like you scan the entire table. This is not recommended most of the time. And query is like when you do like query. But for both of these operations, it will only return 1 megabyte of data for these operations. And it will say like if there are more data, it will say that there's a key called last evaluated key. So it will say that, so this is the key that was last evaluated. So if you want the next set of data, you have to do another request to get the next set of data. So if you have like a lot of data, then you need to think about like how you would handle this. So usually like you need to handle this on client side and not on the server, because like then you will like not like accidentally exhaust your resources on your server by like looping through like a very large set of data. Yeah. Okay. So there's some limits on a single partition throughput. This 100 write request unit, sorry, 1000 write request units and 3000 read request units on a single partition. That means like if you're doing more than 1000 writes or more than 1000 reads per second on a single partition, um, it will get throttled and you won't be able to do that. There's also limitation on if you use local secondary indexes, then your partition size cannot exceed 10 gigabytes. So this is why I said like these are not preferred because of this limitation. So it depends on uh, what your workload is. And one of the main things is like if you're coming from like relational databases, so DynamoDB does not provide aggregation operations like min, max, average, sum. One of the reasons is, as I mentioned, it's built for online transaction processing. So you like it's specifically designed to like it expects you to work on small number of records at a time and not a very large sets of data. And the other thing is like you can't do aggregations because of this limit. So if you have, even if you have a big data set, you can't you can only read part of that at a time. So it does not provide that functionality. And the last thing is it does not provide table joins. Okay. So we'll talk about more on that later. So first we'll try to compare and contrast what we have discussed so far. So relational databases, if you consider use TCP connections, they are persistent. You can use SQL commands, DynamoDB's over HTTPS, and use API operations. Here it's the schema is defined, but in DynamoDB you only need to define your primary key. Your items are basically schemaless. In relational databases, you can access almost all your data and you can query them in different ways using SQL. So SQL is like very rich in those sort of scenarios, like you can do different types of queries. But in DynamoDB, you can only query your items using your primary key. And you can use secondary indexes to uh, like allow additional access patterns, but this limitation. So relational databases are great for ad hoc queries. So if like you can do any type of thing, but as mentioned in DynamoDB, you can access only using keys. Relational database support both online transaction processing and online analytical processing, but DynamoDB is specifically built for online transaction processing. Relational databases are immediately consistent. Uh, DynamoDB offers both immediate and eventual. This is optimized for storage because back in the like storage was very expensive, but now compute is more expensive compared with the storage. Storage is very cheap, so DynamoDB is optimized for compute. So that's why like you won't be able to like very large queries on very large data sets, so it limits on you on that. Here you have foreign keys and you can create table joins using complex queries, but DynamoDB doesn't have the concept of foreign keys or table joins. Okay, so let's answer the question, why no joins? Before that, okay, so yeah, so this is like a preface to this how DynamoDB came to be. So during 2004 Cyber Monday, Amazon.com, they were using Oracle database at the time, and they were hitting their limits, keeping up with the traffic. So this prompted the engineers at Amazon to look for an alternative solution, in-house solution, and they came up with Amazon Dynamo. This is the precursor to DynamoDB. This was like only used internally. And in 2007, they published their findings in a white paper known today as the Dynamo paper. So this inspired kind of the NoSQL, other NoSQL databases as well. Yeah. So what did they find? So they found that joins are too slow and resource intensive at scale. Yeah, something that we already discussed. But this kind of the more important thing, they found that over like 70% of their database operations were on a single record, and another 20% returned multiple rows, but they were from the same table. So all in all, 90% of all of their database operations did not use any joins. So maybe they thought you don't need any joins. Anyway, so before we go to single table design, let's talk a bit about relational data modeling. So with relational databases, you generally normalize your data by creating tables for each type of your entity. So you can use foreign keys to reference a record from one table to a record in another table. So usually you have something like this, like a simple example. You have customers, orders, and you have a foreign key here called customer ID. And then you can use joins to combine these tables at read time and retrieve your desired data. So while this is convenient, joins are very expensive, as we have discussed, and sorry, they require scanning large portions of your database tables and comparing different values. So yeah, kind of performance taxing on your performance. Yeah, so you can join, and so if you try to apply the same concept with DynamoDB and model your database in a relational pattern, so you have to do something like this. So then you have to create a customer table, orders table. Since you have no joins, you have to do one query to get the customers, and then another one to get the orders. Maybe you have to merge them and then respond back. So like this can be a big issue, and so the network I/O can be the slowest part of your application and the limiting factor. And now you are making multiple network requests in kind of waterfall fashion, where one request is necessary for the subsequent request. And as you scale, this gets slower and slower. So this is not recommended with DynamoDB. And so the solution is the single table design. What do you mean by that? You have to pre-join your data into item collections. So if you consider this example, you have users and you have orders and you have profile. But if you can see this, the entire collection has a single partition key called user and the username. And within that, you have two sort keys where one contains the profile information of that user, and another one will contain the order details. So if you want users profile details, you can compare this partition key and this to get this record or this item. And if you want the orders that belong to this user. You can get this partition key and compare up to here. So you get all the orders that belongs to this user Alex Debris. But if you want both, you can have that too, because if you just get by your just the partition key, you'll get everything. So that's how you will like pre-join your data. And by doing that, now we can reduce one of the requests, and we just need to do one request to our table to get all of the data. And so this is basically the concept of single table design. And so you kind of tune your table and design a data model so that your access patterns can be handled with few requests, or ideally should be one. So that's the whole concept. And so just few things to keep in mind. So the first thing is you need to understand your application. So if you are just starting out and things are kind of all over the place, you don't know, like you properly don't know your requirements, you don't know like what you will be doing, like what are the features you will be developing in the next 2 months. If there are a lot of unknowns, then the single table design is not going to be very useful, because you are kind of limiting yourself by defining these key conditions and access patterns. And so if you don't understand your application at the time you're doing this, then there's no point in doing that. So you need to have good understanding of your application. What are the data access patterns, uh, the how like they're getting used, and things like that. And the second thing is you need to create a entity relationship diagram, ERD, and analyze what are the entities in your application and what are the relationships between them, so that you can get a better idea on how to model your data to support different access pattern. What is the best way to model your data? And the third thing is this, the main one, you need to write all your access patterns before you develop anything. So you need to know how you will be accessing your data before doing anything. So basically you need to write like this data will be accessed in this way. So like this key combination can be like a very good one. And yeah, as I mentioned, then you have to model your primary key structure, and you also can satisfy additional access patterns with secondary indexes and streams as well if you want. And you need to get comfortable with denormalizing your data, because like more like all of us are kind of very familiar with the normalizing data. So like it's kind of baked into our brain. And so we try to adapt the same concepts, and that might not be very good when we talk about single table design. Yeah. So when not to use single table design. Uh, so as I mentioned, new applications that you need to prioritize flexibility, and you need to kind of test different things, develop different things. So you don't know exactly what you're going to do. So that kind of scenarios, this is not good. And the second thing is like if your application is using GraphQL, this is not recommended. So I don't have much knowledge on GraphQL, but the reason as I understand is in GraphQL, like you can request different like a set of data at a time, maybe like users and their orders. So what it will do is resolve those two entities separately and try to join them back and send you the response. And that goes against the single table design, and in single table we kind of pre-join so that we only need to get them once. But here, if you use it with GraphQL, so you are kind of getting them twice and it's counting to two, so it's not recommended. And so yeah, we'll talk a bit about how we would model one-to-many relationships. So there's 5 strategies that you can use. We'll talk about one by one so that we can get a better idea. So the first thing is denormalization by using a complex attribute. What does this mean? We'll look at the example. So this one, you have a composite primary key with a partition key and a sort key, and you are kind of repeating it because like this is okay because depending on the context. So like the single table is all about like you are trying to store more than one type of entity in your table. So actually some entities might not require a sort key at all. So in those scenarios, it's recommended to duplicate this. So this is why that is duplicated. And also it's recommended to use generic names for your partition key and the sort key, since like you are having multiple entities. So if you name your partition key as customer, and now you want to store something entirely different to customer in your table, now that's going to be confusing. So the convention is to prepend your actual key with an identifier, in this case customer hash, so that you know what type of data you are storing. And go into this. So this is what is known as a complex attribute. So if you check here, you have a mailing address attribute, but this inside this you have like a JSON object, and you have a home address and a business address. So so this is good when your nested objects are bounded and are not accessed directly. So like if you don't need to access any of these directly, and you are only going to, you are only going to use this to access this item, then this is good. The next one is denormalization using duplicate data. So here's another example. So here we have an author and a book, and in all of these items you have this attribute called author birthday. So for Stephen King, you can see you have 2 books and this is repeated. So this is kind of a no-no in relational databases, but here like it's acceptable if your data that you're duplicating is immutable or they're not frequently changing. But if they are, in any case they're changing, then your application code has to take care of updating them correctly in update scenario. Yeah. So the third one is composite primary key plus a query. So in this example, we have organizations, we have users, and we have metadata. So like if you want to get users for a given organization, you need to compare the like the partition key and part of your sort key. So if you want the users of Microsoft, you'll compare this part and this. So you'll get this item collection. And if you just need the metadata of Microsoft, you need to compare this and this. Yeah. So that's what you mean by uh, composite primary key plus query. So this is the most common when you are dealing with things, and so this can support multiple patterns of the related entities. So for example, if you want both of these, you can get it as well by just using the partition key. But if you want to be specific and just uses, all that access pattern also can be supported. Okay. The fourth one, a secondary index and a query. So this is a bit tricky one. We'll look at the same example, but now we have uh, different entity as well. So we have something called ticket items. Now, since we added this, now we have a problem because now our table can't support access pattern that it previously did. For example, if you want users of Microsoft, you got this and up to here. And if you check the sort key of the tickets, it also has this users hash part. And now if you do the same query, it'll return you the users as well as its tickets, which you don't need because you're only concerned with users. Now that's a bit of a problem. So how can this be solved? Uh, so in this case, you have to introduce a secondary index, in this case, a global secondary index, GSI for short. And in GSI, you can define different partition keys and sort keys. So for this GSI, okay, so before that, you are not going to in this one. So previously, you tried to store the tickets this way, but now you're not going to store the tickets that way. So you are in the base table, your PK and SK for the tickets is going to be ticket hash and the ticket ID. So that's an entirely different item now. You don't have that user stuff here for the sort key. But now you have introduced a GSI, and for the GSI partition key, you have a different one. So you give it like up to like user specific. So you say Microsoft, org Microsoft, user Bill Gates, and your SK is going to be user Bill Gates. So that is how GSI is going to work for user items here, but for your ticket items, you got the same as this org Microsoft user Bill Gates, because like tickets are kind of concerned with a user, so it makes sense to do it this way. And your sort key now is going to be the ticket ID. This doesn't make sense this way, but if you try to query things using the index now, you get a like a whole different view on your items. You have the same data and it's the same items, but now you have this item collection, like the Bill Gates item collection. And here you have the tickets and the user details. Now with this one, uh, if you want the tickets of Bill Gates, you can do this with the secondary index and you can get the tickets. But if you need to get the organ like the Microsoft users, you get the previous access pattern, since like we have changed the sort key of and like the keys of the tickets. Yeah, hope that's clear. Yeah, and so this kind of the similar strategy as the primary key one. So this is good when you need your primary key for something else, and you also need to support this access pattern. So it makes sense you to have index. But you have to remember that you can't create any number of global secondary indexes. So there's a limit on that. It's 5 per table, and it's a entirely different copy of your data, so it's not using the same storage node as well. So if you like if you change item in your storage node, the it will asynchronously update the index as well. So that's how it happens. Okay, so the last one is composite sort keys with hierarchical data. So here we have a different example, and so you have a partition key as a country, and sort key is in a hierarchical pattern. So you have state, city, and the zip. And so with this, if you need you need only the items that matches USA, New York City, you can do that by comparing up to here. But if you want to be more granular and go up to the zip code, now we can do that as well. So it's since you have a hierarchy, you can compare part of it and get your desired items. So this is good for deeply nested hierarchies where you have to search through multiple levels and to get your items. Okay, so then I want to touch a bit on local development. So since like DynamoDB is fully managed, it's available through AWS Cloud. You can access it through the AWS console as well. But the AWS also publishes this Docker image called DynamoDB Local, which is available in Docker Hub. You can like run like an instance of DynamoDB in your local Docker, and you can try out these things. And also there's a tool called GUI tool called NoSQL Workbench for Amazon DynamoDB, which can assist you in data modeling, visualization, and operation building. So these examples are from using that. These visualizations are created using the NoSQL Workbench. Yeah, so where to go from here? If you want to kind of deep dive into DynamoDB, so I would recommend this book. It's called the DynamoDB book by Alex Debris. This was also very useful for me when researching this stuff and learning about DynamoDB. So this is a really good book. I would recommend if you want to do like a bit of a deep dive. And also this Amazon reInvent YouTube, like the tech talk maybe. It's on YouTube. It's called Amazon DynamoDB Deep Dive Advanced Design Patterns by Rick Houlihan. He like both Alex and Rick are kind of advocates for DynamoDB. So they talk about like what are the best practices, what are the best ways to model your data. So if you want to know more about that, I would recommend this. And there's also this reInvent talk. It's called Amazon DynamoDB Under the Hood: How We Built Hyperscale Database by Jasso Sorensen. This talks in detail about how DynamoDB works under the hood and how yeah kind of how they can support traffic at this scale. Yeah, so I think that's the end of the line. Thank you guys for joining and have a nice rest of your day. Thank you. Yeah, bye bye.